So today we will start with the elevation of boiling point. This is the continuation of our colligative properties. The first colligative property that we have discussed in our previous class is the relative lowering of vapor pressure. Okay, the relative lowering of vapor pressure, lowering of vapor pressure and relative lowering of vapor pressure. Both we have discussed in our previous class. Now today we will discuss with the elevation of boiling point. Boiling point elevation. So at first we need to know what boiling point actually is. The question, what boiling point is? Boiling point is generally referred to as a temperature. When we see water, okay, water has a boiling point of 100 degrees Celsius. Now, this is a temperature which denotes that water will change from its liquid state to the vapor state. This is boiling point. What is the other thing? The other solvents like hexane, which are less polar than water, ethanol, methanol, okay, dichloromethane, ethers, they have lower boiling points. So why this difference? Why, when we are telling that different solvents have different boiling points, why is it so? The main thing is that when the vapor pressure that is being applied on the surface of the liquid, the vapor pressure, the vapor of the liquid, which applies the pressure on the surface of that liquid, becomes equal to the atmospheric pressure, becomes equal to the atmospheric pressure which is surrounding it. So when vapor pressure, of a liquid, when a vapor pressure of a liquid, it can be any liquid, becomes equal to the atmospheric pressure, becomes equal to the atmospheric pressure at a particular temperature, then that temperature is known as boiling point of that liquid. Okay, it is known as boiling point of that liquid. So when the vapor pressure becomes equal to the atmospheric pressure, then it will be the boiling point of the liquid. So you need to rise the temperature to that level. Some solvents have a temperature which is 25 degrees Celsius. You do not need to heat them. We'll just keep it there, and you will see that it is getting even the amount of solvent, means the volume of solvent, is steadily decreasing. Okay, so you will find in that way. Now the next part is, so this is boiling point of any liquid. Now how will you increase it? How will you increase the boiling point? In order to increase the boiling point, what you have to do? You have to increase the temperature to the extent, means first what you have to do, you have to decrease the vapor pressure. At a particular temperature, you have to decrease the vapor pressure. Suppose at 100 degrees Celsius, the 100 molecules of water from the surface comes up and gives the pressure to the liquid surface, water surface. Now, at 100 degrees Celsius, you have to do something inside, you have to do something with the water so that instead of 100 molecules, there should be 70 or 80 molecules. Okay, instead of 100 molecules, there should be 70 or 80 molecules. Why? Because lower number of molecules above in the vapor state, posing the or giving the vapor pressure should be less. Less number of molecules are there, less vapor pressure will be there, and you have to elevate the temperature more so that the 100 molecules of water should reach to that surface and gives the pressure which will be equal to the atmospheric pressure. So this is how you can increase its temperature. So in two ways you can do it. You have to put someone between the layers of water so that they can actually hold some of the molecules towards itself. Okay, they have to hold some of the molecules towards itself so that few molecules will go up and the others will not. Others will stay down. Understood? The others will stay down, and the others few molecules will go up and few molecules will be down. Means among 100 molecules, 70 can go up, 30 will stay down. You have to elevate the temperature of the solvent so that the other 30 will also go up. So this is one way. What is the other way down? The other way is that you will try to make that thing, means if you have to increase the pressure, you have to increase the pressure of the surrounding. If you could increase the pressure of the surrounding, so at one time the 100 molecules which are coming up will be thrown down, because we know that with increase in pressure, volume decreases according to Boyle's law. So if the atmospheric pressure, if the surrounding pressure is higher, then you need more number of molecules so that it will equate the pressure of the surrounding. Okay, that is why you will see in hill station where the pressure is generally low, liquid boils at a, when if you see someone boiling liquid for making tea or making a boiled egg, okay, you will see the temperature of the liquid is sorry, the water is boiling at a lower temperature than 100 degrees Celsius. Okay, this is what happens in the hill region where there is the pressure is low. So either you have to increase the pressure or you have to put someone between the layers of water which will hold some of the molecules together. So this is, by these two ways you can elevate the temperature, elevate the boiling point, elevate the point where the vapor pressure of a liquid becomes equal to the atmospheric pressure. Okay, we will come to it later, but let us first know this, that elevation of boiling point, the boiling point of the liquid is the characteristic temperature. We have discussed that. So addition of a non-volatile, now we will come to the part. We will just add addition of, yes.
ওই জিনিসটা রিপিট করতে পারবে, প্রেসারের জন্য কি হচ্ছে, মানে হিল স্টেশনে যেটা বললে এক্সাম্পল দিয়ে?
Absolutely, একদম। So hill station, যখন আমরা হিল স্টেশনটা দেখছি, when we go to the hill station we will see that জলটা খুব তাড়াতাড়ি গরম হয়ে যাচ্ছে। when if you see someone is making Maggie or someone is boiling egg, so the temperature means they are just heating up the gas light, and in a very few amount of time, okay, it will take like 2 to 3 minutes to for the water to get boiled, it will to reach the boiling point, it will start to boil. Now another example is that if you put water in a syringe, if you just hold the mouth of the syringe like this, means the tip will be here and here you will put water and just pull the syringe up, then you will see the water starts to boil, because you're decreasing the pressure inside, and the amount of vapor that there is, they are enough to equate with that atmospheric pressure, surrounding pressure, and the water will start to boil. Okay, so in the hilly region the pressure is low, so lower pressure we have already learned in Amonton's law. Okay, remember about the Amonton's law. Amonton's law states that pressure is directly proportional to temperature if volume is constant. Okay, Amonton's law states that pressure is directly proportional to temperature if volume is kept constant. Okay, so this is the thing that happens in the hilly region. Pressure becomes lower, so temperature of boiling, means the boiling point also comes to a lower point. Okay, means to a lower temperature. Understood? বোঝা গেল?
Yes, sir. হ্যাঁ।
Now, so addition of a non-volatile solute, if I am adding addition of a non-volatile solute, addition of a non-volatile solute in a solvent, non-volatile solute, it can be NaCl, okay, it can be anything which is soluble in water, any salt which is soluble in water. Addition of a non-volatile solute in a solvent lowers its vapor pressure, lowers its vapor pressure. Okay, so first criteria was lowering the vapor pressure, so the first criteria has been managed. Okay, therefore more heat will be required to increase the vapor pressure, therefore more heat will be required, to elevate the vapor pressure. Okay, so this is how you will increase the vapor pressure. Now, so initially it will be TB, initially it will be TB0, let TB naught, and the final be TBF or TBI and TBF, you can say like that also. Initial and final. Okay, initial and final. This is initial and this is final. So it is changing to this part. Okay, it is changing to this. Therefore, del TB. Del TB means the change in boiling point. Del TB means change in boiling point. This del means heat. Okay, and this del means change. Okay, change in boiling point will be TBF minus TBI. TBF minus TBI. This will be the change in boiling. Final boiling point after addition of solute and non-volatile solute, absolutely. And this is initial, means without the solute. So this is the change where you will be seeing that it is going in that fashion. And this will be TBI. Now, this del TB will be directly proportional to the amount of solvents, means the molecules, the mass, everything. So that will be correlated to actually that will be correlated to a concentration term which will be known as molality. Okay, it will be known as molality. It will be correlated to the concentration term of molality. Now we all know that if we remove the proportionality sign, there will be a constant. Here it will be Kb and times m, molality. What is Kb? This is molal elevation constant. Kb is molal elevation constant. Molal elevation constant. Molal elevation constant. And that another name is that, or ebullioscopic. Ebullioscopic constant. Okay, most important thing, its unit, Kelvin per mole per kg. Kelvin per mole per kg. Okay, this is the thing. So the molality is mole per kg and this is Kelvin per mole kg. Okay, Kelvin per mole kg. So you can see that if you multiply them, this per mole and kg and per kg will cancel out each other and you will be left with Kelvin. So this is the end. Now, like in our previous video, we have already discussed that molality in this case can be written as WB by MB, okay, divided by 1000, sorry, WA by 1000. Okay, this is WB by MB means weight of the solute by molecular weight of the solute, weight of the solvent by 1000 means whenever we are doing something, suppose we are taking 1 liter of water, that means for molality, in this case, for molality, it will be WA, which is means weight in grams. Suppose you have given 100 grams of water. Okay, 100 grams of water. So you have to convert this 100 grams to kg. 100 by 1000, it will be kg. Okay, so in molality, we know that number of moles per unit kg of the solvent. Number of moles per unit kg of the solvent. So for that reason, it will be WA by 1000. So it will be simply Kb into WB by MB into 1000 by WA. You can also write it in the in a fashion in Moore's book. It has been given WB by WA times 1000 by MA. Okay, we can also write this, but sorry, MB, not MA. It will be MB. So you can also write in this fashion, but it's not required. You can easily do the things that is there because you don't have to go for fascination. You just have to learn the logic. Okay. So no need to memorize anything. Just follow.
Sir, what is WA and WB?
WA is weight of the solvent taken in grams. Okay. And
Okay.
WB is weight of the non-volatile solute in grams. Okay, weight of the non-volatile solute in grams. Understood? And MB is molecular weight of the solute. Okay, MB is molecular weight of the solute. Molecular weight of the solute. Okay. Now, next thing is we have to learn about that depression in freezing point. So elevation of boiling point we have done. Next thing is depression of freezing point. So depression, we all know we are very familiar with this term depression. Okay. Depression of freezing point. It is similar, not same, but similar to that what we have discussed in the elevation of boiling point. It is similar to that. But here what happens that depression, freezing point. What is freezing point? Like boiling point, you know that the atmospheric pressure should be equal to the vapor pressure should be equal to the atmospheric pressure. So what is freezing point? If I ask you, then you will say that freezing point of a liquid is the temperature at which vapor pressure of a solvent in its liquid state and vapor phase become equal. Okay, vapor pressure of a solvent in its liquid state and vapor phase becomes equal. Okay, you will write vapor pressure will write vapor pressure of a liquid, or you can write solvent as well, vapor pressure of a liquid or a solvent. Okay, in its liquid state and vapor phase, in its liquid state and vapor phase becomes equal. Okay, so freezing point is the temperature at a becomes equal at a particular temperature, which is the freezing point. Okay, which is the freezing point. So freezing point is the temperature, freezing point of any liquid is that temperature at which the vapor pressure of a solvent and its liquid, means vapor pressure of a solvent in its liquid and vapor phase becomes equal. Now, what is the meaning of the vapor phase? Means vapor pressure of a liquid or a solvent in its liquid phase and vapor phase are equal. What does this mean? This means that whenever you are having a vapor pressure, okay, a vapor pressure in its liquid state, means when it is in the liquid state, pure liquid state, the vapor will be just above it. Okay, just the above vapor, that pressure it is applying will be very negligible, means very less amount of in pure liquid state. How many vapors will be there? Negligible means 1 or 2 or 10 molecules will be, means in most cases it will be 1 to 10, not more than that. Okay, few molecules, only few of those molecules will give the vapor, will give the pressure. Now these pressures, this vapor pressure this is in the liquid state, and same amount of pressure will be given between, means one vapor pressure, one vapor molecule is also giving the pressure on the other vapor molecules. One vapor molecule is also pressing over the other vapor molecule. So that pressure, okay, individual pressure means suppose one is lying above and above which 2 or 3 are giving the same pressure, and same pressures are given by 2 to 3 liquids over 2 to 3 molecules over the liquid surface. So suppose you have 10 molecules, 4 are putting pressure on one and the other fiber putting pressure on the liquid surface. So this is how you will say that the vapor pressure in the liquid phase and the gaseous phase in the vapor phase are equal. Okay, so that temperature, and for that to happen, you need very low temperature, because at higher temperature, more number of molecules will move up. So in order to reduce the number of molecules to leave the water surface, the temperature should be very low. Okay, because you cannot change the pressure. So you have to change the temperature. Temperature should be very low in order to achieve that. So that is why, and that in that conditions, you will see that for sealing the vapor, for sealing the molecules to not move in the vapor phase, the liquid gets tight together, holds each other tightly such that they form a strong sheath, and that strong sheath is known as ice. That is why they are tightly packed to each other to reduce the vapor pressure at that particular temperature. And we say that temperature as the freezing point, or the point where the water molecule becomes ice. Okay. Now the freezing point, is it clear? Did you got it? I think it is clear. The freezing point of a solvent decreases on addition. Similarly, freezing point will also decrease by addition of a non-volatile solute, because temperature, the amount of temperature that is required to lower the vapor pressure, lowering of vapor pressure, you need some vapor molecules also. You need to give some vapor molecules also to put the pressure on the molecules. So that is why you need to lower the temperature more, so that the liquid molecules, far less liquid molecules, goes up. Okay, so the freezing point of a solvent decreases on addition of a non-volatile solute. So non-volatile solute decreases the freezing point. Non-volatile solute decreases the freezing point. Okay, so it will be same del TF this will be TF initial minus TF final. Okay, why initial minus final? Because initial is higher than the final. But the rest will be same. TF equals to KF into M. In case of KB, it will be KF, and KF is molar freezing point constant, molar depression constant, molar depression constant, or it can be also said as cryoscopic constant, or it can be also said to be cryoscopic constant. Okay. Similarly, we will write Kf into Wb by Mb times 1000 by Wa. Okay. Wb by Mb times 1000 by Wa. You will write that and you will get the value. The third part, the third colligative property will be our osmotic pressure. Okay. Osmotic pressure. This is the third colligative property, the osmotic pressure. Now, what is osmotic pressure? Osmotic pressure of a solution. Suppose you are having a solution, osmotic pressure of a solution at a particular temperature. You are having a particular temperature. It can be room temperature. It can be an elevated temperature. Let us assume that it will be room temperature. Osmotic pressure of a solution at a room temperature, at a particular temperature, is the hydrostatic pressure that builds up. It is the hydrostatic pressure. It is the hydrostatic pressure that builds up. The hydrostatic pressure that builds up. What does it build? Builds up when the solution is separated from the solution. When the solution is separated from the solvent. When the solution is separated from the solvent by a semi-permeable membrane. Okay, semi-permeable membrane. Understood? Osmotic pressure is generally denoted by this sign pi. Okay, osmotic pressure is generally denoted by the pi sign. Okay. We have learned about the ideal gas equation PV equals to nRT. This will get modified. Okay, and you will write here pi V equals to nRT. This is the osmotic pressure or Van Hoff equation. Van Hoff's equation. Okay, it is the Van Hoff's equation. Pi V equals to nRT. So N is now N is number of moles. N is the number of moles. R is the gas constant. Okay, T is the temperature and V is the volume. So N by V RT, if you write it like this, then you will get CRT, where C will be equal to the concentration of the solution. Okay, T will be the concentration of the solution. This moles per liter, it will be generally it will be molarity. Okay, now what are the conditions for validity of this Van Hoff equation? There are two conditions. Okay, conditions of validity. Conditions of validity for these two Van Hoff equation. So first, it should be a dilute solution. It should be a dilute solution. It should be a dilute solution. If it is not a dilute solution, if it is a concentrated solution, then it cannot differentiate the osmotic pressure, because hydrostatic pressure will means it will not be able to distinguish between the hydrostatic pressure when it's build up and when it is not in the process of building. How it is working, it's very difficult to identify if the solution is concentrated. Okay, it's valid for validation of the equation. Concentrated solutions are very hard to give you the right values. Okay, you have to be very careful to actually measure the values. Now, second is solute neither dissociates nor associates. The solute molecules should neither dissociate nor associate. Okay, this is a very important thing. Okay, suppose you are adding a non-volatile solute and it is NaCl. Okay, non-volatile solute and it is NaCl. NaCl dissociates. NaCl dissociates to Na plus and Cl minus. So as Na plus dissociates between Na plus and Cl minus, you will say, will it show a right value of osmotic pressure? Answer is no. Okay, the answer is no, it will not, because if it dissociates, then it will not, the conditions will not be matched, and not the conditions are drafted after doing such calculations, after performing experiments to a vivid manner. Because in chemistry we do not give a theory on the basis of a guess, we give the theory on the basis of experiments. We have to do lots and lots of experiments. Actually, we have to go through lots of experiment to actually validate this type of conditions. Okay, we cannot make a guess that okay, let it be like this. Assume, no assumption. These are all based on experiment. Chemistry is based on experimentations, not assumptions. Okay, so this is solute. So there is no delulu here. Okay, now the next thing is what type of non-volatile solute should we use? The type of non-volatile solute we should use is like sugar. Okay, suppose you are using sugar inside it. Suppose you are using an acid, HNO3. We will discuss about all the acids and the other things in two different aspects. One, how it occurs, means how Raoult's law actually means behaves whenever in a solution you are adding a non-volatile solution which neither dissociates nor associates. This is the first one, making some hydrogen bond and other things. Second one is that if it dissociates or associates, then it will give rise to abnormal colligative properties. It will give rise to abnormal colligative properties. But before we are ending this, I must show you that there is an isotonic solution where the two osmotic pressures are equal. If I have two solutions, pi 1 and pi 2, okay, if two solutions, if both have same osmotic pressure, then they will be called as isotonic solution.